it gives me very great pleasure to welcome Dr. Charles Kennel. Charlie has a very long and distinguished career, both as an academic, but also as a leader in the arena of astrophysics and earth science and planetary science. He's the 9th director of Scripps Institution of Oceanography at the University of California, San Diego. And he also serves as UCSD Vice Chancellor of Marine Sciences, the Dean of the Graduate School of Marine Sciences, and a Professor of Physics at Scripps. Dr. Kennel was born in Cambridge, Massachusetts, and received a bachelor's degree in astronomy from Harvard College in 1959 and a PhD in astrophysical sciences from Princeton University in 1964. He was appointed Associate Professor of Physics at UCLA in 1967 and a professor in 1971. And Dr. Kennel became UCLA's Executive Vice Chancellor in 1966. Sorry, 1996. Sorry, Charlie. Well, that's totally thrown me, but where was I? Yes. But in between, before he took up that appointment, from 1994 to 1996, Charlie served as Associate Administrator for NASA, directing Mission to Planet Earth, the world's largest earth science program. And he chaired the National Academy of Science National Research Council Committee on Global Change Research from 1998 to 2001. And he's currently serving his second term of chair of the NASA Advisory Council, and he recently served on the Pew Oceans Commission. So he's really ideally suited to talk to us tonight about something very important, I think, that's happening in science. In fact, you might characterize it as a paradigm shift in how scientists study our planet. Before I introduce Charlie and ask him to speak on global Earth observations, the view from SIO, I just want you to know that he's had numerous awards from not only the States but all over the world, and he's also the author of over 250 scientific publications. But you've come here tonight to hear Charlie speak, not me, because it would take the whole of the rest of the evening for me to get through his achievements. So without further ado, I'm going to ask Charlie to talk to us tonight. Thank you.
Well, thank you very much. I'd like to thank you all for coming out on such a rainy evening. And I must say it is a pleasure to give another in the series of lectures that was named for our good friend and colleague Jeff Graham, who did such a marvelous job as a pinch hit director of the aquarium several years ago. When I first offered to give this talk, I had no idea that it would become as timely as it is today, this very moment. My discussion is going to be about Earth observations from space and the new way that the world is thinking about undertaking observations of the complete Earth. Let me start. It's only been in the last 2 generations that we really have understood the extent to which our human activities have transformed the Earth. If you look at this picture, this is a synthetic clear sky photograph of the entire Earth at night. And it shows the city lights from space. This tells you where human beings are being active economically, where we're using our energy. And in fact, we're putting off so much light that the Earth now is a chemosynthetic star. But I think this gives you just some sense of how pervasive the human influence has become in the last 50 years on the surface of the Earth. And it's no surprise that during the same period of time, concerns about global environmental problems emerged. We hear now every day in the newspaper worries about global water availability in the future, the ozone hole, the globalization of air pollution. What was once a problem for Los Angeles and Mexico City is now spreading across entire ocean basins. Climate change, how can you miss that one? how can you miss all the talk about the decline of biodiversity and ecosystems? So as our influence and our activity level grew, so also did the impact we had on the surface of the Earth. About 25 years ago, the earth science community went through a major change, and it added to its traditional study of the geology and the history of the Earth, it added a study of these problems, of the contemporary Earth. And they developed a new name, which we now call Earth System Science. It is a study of all the interacting parts of the Earth with a focus on those problems that are of importance to us as a civilization, both now and in the coming century. And so here's NASA's view of it. Weather, Earth's surface and interior, that is to say earthquakes, climate change, the carbon cycle and its effect on ecosystems, changes in the atmospheric composition, the water and energy cycle. And so it is that this was a scientific response to developing the studies needed to address those large problems that are emerging on a global scale. So now, in addition to dealing with the eons of the past, we have a new focus on the geological here and now, the next 100 years. And we're creating an interdisciplinary panorama of the Earth, as it is today and as it will be tomorrow. Earth, atmosphere, oceans, ice, living things, all in interaction. We're also taking into account the way we human beings are influencing the Earth system. It's now the case also that after 25 years, Earth system science is beginning to make useful forecasts, just as we've been able to do with the weather for the last 50 years. And this entire enterprise of Earth system science requires a comprehensive Earth observing system of global scale. Global scale. What is a global Earth observing system? It is, of course, very large and very complex. But it can be split up into 4 basic categories of activities and endeavors. The first, and the one that precedes all others, we must construct the human architecture, the relationship between the people who collect the data and the people who need the data and the human concerns. We must develop the human architecture and get the people who will build the system and the people who want the system to talk together. Human architecture precedes system architecture. But the system itself, the scientific system, consists of networks, multiple sensors of different kinds that I will describe. It consists of the cyber infrastructure that will manage unprecedented quantities of information about the Earth, and none of this technology would make the slightest bit of difference unless we did not put it to work creating systems that will support our decision makers as they learn to manage our environment and the world's ecologies. So let me start then with human architecture and the developing international framework for it. In the United States, the work started at the official level about 5 years or maybe 10 after the scientists began to develop Earth system science. And the expression of Earth system science in government policy was the Global Change Research Act of 1990 in the first Bush administration. This was the first time that the words global change appeared in government language. And this act called for global measurements on all relevant space and time scales. And it called forth the most comprehensive satellite observing system yet thought of for Earth observations, the one that I was privileged to help manage while I was there at NASA a few years later. It was at that time that we at NASA, working with the White House, developed a new dimension to the observing strategy, which was to make it go international. So that the White House then created a working paper entitled the Global Observing Strategy, the International Global Observing Strategy, an internationally coordinated system of space-based and in situ data acquisition, archiving, and distribution system. But this was a human architecture step. It was not to build the system, it was to get the scientists and the technologists from all of the world's countries together to figure out how you would merge data from space, data from the oceans, data from the atmosphere, and data from the land into one comprehensive system. This process of international engineering design proceeded for the next few years. But very recently, there's been a major breakthrough at the highest political level. At the Avion, France summit of the G8 nations, the world's 8 largest economic powers, the United States and subsequently the G8 proposed that the world create a global Earth observing system of systems. They proposed that these large economies and many others from around the world coordinate their various global observing strategies. This was followed just 2 months later by an Earth observing summit that was opened by Colin Powell at the State Department and attended by the Secretaries of State of 34 nations, in which they agreed that they would all work together to create global Earth information as a basis for sound decision-making. So now the purpose of creating this system was not simply to satisfy scientists' curiosity, but it was to provide the basis of information that the nations of the world would need as they make the tough calls about the global environment. They created 5 international working groups that worked throughout the year, and in April of 2004, they adopted a framework document for the 10-year implementation plan. And in February of this year, February 16th, I believe, the nations of the world will sign this agreement. At the present time, in November, there were 53 nations now that had signed up. The present number, I believe, is 55. You will see amongst these nations the world's largest scientific powers and many, many smaller countries, all of whom are essential to the concept because it will be their territory and their people that will be deploying many of the instruments that are needed in the global system. In addition, there are 34 international scientific and other organizations connected to the Global Earth Observing System planning process. Of these 34, there are 2 that are associated with the oceans and closely with us: the UN's Intergovernmental Oceanographic Commission and the Partnership for the Observation of the Global Ocean, an association of 25 of the world's largest oceanographic institutions, of which we were the founder. Now, to summarize then, the human architecture is developing, starting with the government organizations that represent the people that are going to generate data. This architecture is not yet complete, but the international framework for coordination is beginning to be there. But at the same time, I must point out that there's been not too much contact between the government agencies, the universities, and the users and other scientific organizations and the users who need the information. The human architecture must be completed by making sure that there is participation of the users at all levels. So now let's move on. What is it that these large agreements are going to facilitate the creation of? Well, let's start with the multisensor networks. It's the whole enchilada of Earth observation. It's remote sensing from spacecraft and aircraft. It's in-place measurement. It's every platform available to our technology: spacecraft, aircraft, ships, moorings, floats, and more. It is every kind of sensor, active sensors, radars, lidars, passive sensors for physics, chemistry, and biology. It is complete coverage of the oceans, the atmosphere, the land, and the ice. And we must develop the capability to move back and forth, to shift our focus from the entire globe to our region, to our local, and back to our local area, and back again. Here's an example, a timely example, of an observing network. This is just one of the observing networks whose data will be included in the overall system. This is the International Tsunami Information Center for the Pacific. You all know they didn't have one in the Indian Ocean. What you see is a collection of sea level stations maintained by agencies in the United States and Japan, Australia, distributed mostly around the coastlines of the wealthy countries, with a few stations in the middle to track the propagation of the tsunami waves as they cross the Pacific. There is a coordination center in the middle of the Pacific in Hawaii. And this center knew within an hour of the tsunamis, of the earthquake that caused the tsunami, that there would be one. They notified every one of their people on their mailing list with the press of a button, and then they asked whom they should call in India and on the Indian Ocean basin. And that part, the completion of the observing system and the connection to the users who needed it, was not made in the case of the Indian Ocean. Now, we asked ourselves, what was Scripps' role in the development of tsunami observations? We went back to the original source, Walter Munk, and he told us that in 1947, actually, he, Walter, with his colleagues, built the first true tsunami detector, which was a simple hydraulic pressure gauge that was designed to respond to the very low frequencies and very long wavelengths of the tsunamis. That between the tides, which are 12 hours, and the ocean swell, which is a few minutes. Now, in 1948, Francis Shepard of Scripps sat on the National Research Council committee, and he that committee made the first recommendation that a tsunami warning system be created in the Pacific. That was not created until after the great 1964 earthquake in Alaska, which did send a tsunami all across the Pacific. Some of you may recall that it destroyed a good part of the city of Crescent City in Northern California. There was a tsunami warning here in La Jolla. There was a connection with the users. The police asked people to evacuate, but Walter wonders whether that was effective because as many people were seen going down La Jolla shores to watch the incoming waves as were seen going up the hill to try to escape. And so even if you have the observing system, and even if you have the ability to warn the people who need the information, they don't always listen. Our first head of the Hawaii warning system was a Scripps graduate, and others of us have been working on it for a long time. Now, this is a 40 station network observing earthquakes around the world, and this is at the various stations the recording of the earthquake that generated the tsunami. This arrived within minutes of its occurrence at the different stations and at Scripps. Now, with seismic information of this support, you can record the earthquake almost immediately, and this can be, we could have known and suspected that there might have been a tsunami within minutes, and we did, within minutes of recording of this, that with good measurements of the shape of the ocean bottom and good numerical computations, it is possible to go from the seismic information to estimating where the tsunamis might go, and with ever more precise information about the shape of the coastline and the bottom near the coasts, you can get ever more precise predictions of how the waves would develop. So this leads us then to our next comment, and that is that rather than build a special system for monitoring tsunamis in the Indian Ocean, it's probably this time going to be more efficient to build on what is already being planned and what we expect ultimately to be incorporated into the global observing system, and that is the National Science Foundation's new Ocean Observatory initiative, which is a project that will be funded, we hope, in the year 2006. And this little diagram displays all of the capabilities that the NSF and we foresee will occur in the ocean observing system. Ocean bottom observatories connected by powered cables carrying information, moorings tied to the bottom, large buoys and spar buoys, and of course ships fundamental to the deployment and the whole enterprise, all of them in great contact with satellites. And it's no surprise, but very pleasing to me that the NSF chose to place their communications center somewhere near Scripps in Southern California. And so we think that these comprehensive observing systems that will go forward and serve many scientific purposes and many practical purposes are in fact the framework on which a modern tsunami detection system could also be deployed. And then you combine it with the seismic observations and numerical modeling, and we think you can do a good job now on a global basis. And that may be one thing, one positive outcome of the global Earth observing system. Another part of the system we must never forget are the satellites that look down on the Earth from above. This is the NOAA contribution. NOAA, the Department of Defense, and NASA, and the European Meteorological Satellite Agency have all gotten together, and in around the year 2010, we'll start deploying a comprehensive system for observing both the weather and making important and highly calibrated measurements that can track the changes in our climate. And so combining the observations from space with those from the surface of the Earth and below the surface of the ocean will be very important. Now, one thing I think you can see from the scale of the enterprise that I illustrated in those pictures is that today's sensors and platforms are still pretty big objects. They require substantial infrastructure for power, communication, deployment. But think of the possibilities when, in the future, there will be millions, literally millions, of small sensors deployed, especially on the Earth, each radiating their information back to us, basically via cell phone. And it will be at that time, not when there's a few thousand users and producers as now, but when there are millions of users and producers who are collecting very detailed information and communicating it and then receiving back the decision support information that they need. It will be at that time that this system is mature. Now, the other part of the system where we at UCSD are very fortunate as well is in cyber infrastructure. It's a very broad term, but it really means the whole enchilada of information managing. It means very high capacity computing, not only for the data reduction, but for the data management. It means communication of very large volumes of information of very many different kinds between many different centers. It means the large numerical modeling of the type that I described for the propagation of tsunamis. And it means conveying all of this information with advanced forms of communication, such as that that you see here at our visualization center, where you can see at a glance what these vast computations are saying. Now, I'd like to make a comparison between the present state of our thinking about Earth observations and what we now know to have happened with the Internet. It may come as a surprise to you, but the first Internet experiment was done in 1969, and throughout the 1970s, it was managed by the Defense Department as a means of secure communication during a possible disaster or nuclear attack. And it was the whole uses of the Internet were controlled by the government. But by the 1980s, my colleagues in the high-energy physics community, who had a great deal of technical sophistication themselves, began using this ARPANET for their own purposes, and they started exchanging data and plans over an international network. And the important thing was that while the government supported their work, it did not determine the usages of the net. This was the first peer-to-peer system. They could decide what they wanted to do with it. And it was within only 4 years that the first web crawler and the first Internet standards were designed, and that was about 1992 or 1993. And about a decade later, this has close to 1 billion users, and nobody, not a single individual who thought about the Internet, had the slightest idea about the vast number of uses to which it would be devoted. Now, is the Global Earth Observing System, this international project, going to follow a similar path? We've already been through phase 1, government command and control projects, and right now we're beginning to enter phase 2. In phase 3, we can see some of the technical evolution that will be needed. Grid computing, collective computing by a distributed network of the world's computers, all working together on similar problems and sharing each other's codes. In fact, at the present time, under the leadership of our UCSD's Cal IT Squared Institute, the California Institute for Information Technology and Telecommunication, the nation is already fabricating the basis for phase 2. This is the so-called Lambda network, which is a high-capacity set of cables that will enable the exchange of very large amounts of data between the major research institutions in the United States. This will be the beginning of a real peer-to-peer usage of Earth observations and many other things. And you can see Scripps and UCSD in the lower right-hand corner. Now, suppose you build all of that. What then? Does it make any difference to people? Will a few thousand scientists be made happy? Well, the answer is yes. But will it justify the effort? The answer is no. We must connect the global Earth observing enterprise to effective decision support systems. Turn this information into knowledge and understanding related to the things that people care about or worry about. And if we can do that, then I believe providing this depth of, on a 7x24 basis, providing this depth of information to the millions of people who need it will become a principal tool by which our society evolves to achieve sustainability on a global scale. And it is for this reason that the international negotiators defined the reasons for doing this in terms of 9 global societal benefit areas: disasters, health, energy, climate, water, weather, ecosystems, agriculture, biodiversity. Big issues that everybody in the world cares about. But the other aspect of it is that we are also beginning to understand how these big categories of need actually are connected to local questions that we care about. We care about the health and safety from natural disasters. We care about risk management. We care about how to plan our infrastructure against the long-term predictable changes that we now can foresee in our environment. We care about many of these things. And it is only when the information and understanding from the global Earth observing system actually speaks to the issues that people care about that it will be effective. Obviously, one simple example that we at Scripps have been working on for many years, we have one of the first group, were the first to identify the El Nino phenomenon and a larger scale effect that's affecting us now, the North Pacific Oscillation. These are natural variations in the climate, but it is now possible for us to predict with some accuracy, and we are doing it today, to predict with some accuracy how these natural variations in ocean climate can affect our energy demand and our water availability over the coming years. Other examples where people need the knowledge gained from Earth observations, offshore oil exploration, obviously, good maps of the ocean bottom, fisheries productivity. Information about the entire ecosystem is needed to intelligently manage our marine resources. Now, in all of this, I should point out that the role of the scientific community is changing, and it's evolving, and it's becoming broader. Our goals, our original goals, are still there. Originate the science, create the models, develop the observing technologies. We still do that. We've been designing the observing strategies and systems that underlie these negotiations for the last 20 years. We've been transferring those designs and technologies and so forth to both the public, that is to say the government, and the private sector. But there is now a new role for us as scientists and a new adaptation that our universities must make. Because in the future, we will be partnering in the governance and the management of long-term observing systems. And we will be playing a key role in the conversion of the knowledge to decision support systems involving practical users on a 7x24 basis. They will want us to do that because they'll need us to infuse new objectives and new technologies into this single, vast global system. And in this way, as we develop new observing capabilities, we will also develop new users. So, in order to do all of this, our research community and we at Scripps are becoming more multidisciplinary and more service-oriented. The human architecture still needs to evolve. We're embarking on phase 2 of the Earth observing system. Large, sophisticated science and technology users, but phase 3 still needs to be developed. And the universities and we at Scripps are going to play a very significant role in moving from phase 2 to phase 3. This is going to require for all of us at the government and within the university and within Scripps new management concepts. I can't even describe them logically, but I can tell you some of the words that go with these concepts. System of systems, multi-sector consortia, standards interoperability, open communication, evolving, adapting, education and outreach. These are the words that people are using, that they are trying to now mold into a management conception that can deal with what is the largest system engineering project ever undertaken. How are we going to respond to this opportunity and this obligation at SIO? We propose to create a Center for Earth Observations and Applications at Scripps. It will be open to participants throughout UCSD. It will be led by our Deputy Director for Research, John Orcutt, who has played a very great role in designing many of the ocean systems and geophysical systems that are already on the drawing board. And I must say that if you combine the comprehensive observing capacity of Scripps with the great ability to manage information both here and at Cal IT Squared and the San Diego Supercomputer Center, and you look at the programs in engineering and chemistry and in the other parts of the campus, it is quite possible that UCSD is unique in its ability in that it will have within the walls here an example of every activity that will be contained in the global system. Our mission will be to do at UCSD and in La Jolla, do it first and faster than the international system because we're smaller and more agile. And then as a result of that, we can be an effective participant, an important participant in this global Earth observing enterprise that's going forward. The new management concept, this is not going to be a single institute with a director and all of that. It's going to be an internal venture capital group that will develop the system of systems within UCSD and SIO that corresponds to the system of systems at the international level. So let's step back a bit. What is it that's really happening as we look over the array of scientific enterprises that have developed over the last 20 years? The major developments have been in Earth system science. They have been in information technology, and they have been in modern biology. And what you see happening today is a convergence of all three. And this convergence is leading us to an entirely new conception of what science can do. Originally, we were happy to be able to understand how the Earth system behaves, to be able to describe it to people, to know the physical principles that guide the events that we see. But the new goal is continuous awareness of the state of the system, 7/24 every day, knowing what all of the Earth systems are doing, and knowing how we as a civilization are interacting with those systems on a 7/24 basis. We are going to be able to use continuous awareness to manage our resources, our environment, our response to disasters. And continuous awareness, widely communicated, will promote integrated responses amongst the world's nations to dealing with our emerging global environmental challenge. And so you can see that we're going to need one. You can see that there will be created at most one global Earth observing system, and that our need will be there for a very long period of time. We are today beginning an endeavor that will evolve over the entire 21st century and will have to endure as long as we have an advanced civilization. So thank you very much for coming. Would I care to make any comments about the issues concerned with global warming? Well, yes, indeed. This is the most enveloping environmental problem of them all. And it is because we are beginning to see the way in which human beings affect the climate. Now, the climate is a broad name for the physical and conditions that affect all of the living systems in our ecologies. And it is global. Every human being on Earth, every nation, every political entity, every business is surrounded by their local climate. And so And the evidence that we are changing the climate is, within the scientific community involved, sufficiently compelling that we believe the problem needs to be addressed. First and foremost, we must develop an understanding of what will happen in very great detail to the things that we care about. So we have to go from global models of the climate evolving over the next 100 years to models of what will happen in California, what will happen to various industrial sectors, and we must begin to develop our capability to answer the most important question in environmental science. What's going to happen to me? Now, the basis, the Bush administration has been a very strong proponent of this Earth observing system. And it is because they believe it will provide an important and solid basis of information for which will make decisions, will support decisions better in the future. And so this has been one of their main contributions, I believe, to the climate issue. But you will note that the international negotiators identified 9 societal goals, of which climate is one, that this comprehensive system will have to address. This, I believe, is the right way to look at it as well. If I can, that I have portrayed this large Earth observing enterprise as a tool for government decision making. And how do I square this with the fact that there are very many people now that don't believe in the theory of evolution and object to plate tectonics and so on? And these are really 2 separate questions. First, I did say that I felt we were entering phase 2, in which the major interactions, there would be interactions between the major users. And the governments at present believe that the real purpose of phase 2 is to support their major decision-making and their treaty-making with regard to large issues like global warming. But I've also argued that the system will become truly effective when it supports the decision-making of all sorts of groups, and at the time when people have access and understanding of enough information from this system that they themselves will be able to develop their applications and uses of the knowledge and find their ways to support their decisions. So I think phase 3 is a totally different phase in which many, many more people and many, many more businesses have access to the understanding generated. What do you do about the people that, for a variety of reasons, don't listen to predictions of science? I've gotten this question in many forms in the past, and what I have said is something like this. You know, if we are right in our scientific assessment, say on an issue like global warming, events will unfold. And they will occur, and gradually, one by one, as is occurring now in the Arctic, people will be able to perceive that there is a change, that the climate is changing. And one by one, they will sign up. So the important thing, I think, for us as scientists is simply to state do the very best we can with the most objective presentation at all times of the facts and of our best understanding. And as part of that endeavor, making the information widely and broadly available from all of the Earth observations that we can make, and make them available to anybody who wants to take a look at them and to test our hypothesis. That is an essential part in building the confidence about the changes that we predict will happen. Some of the things that we're going to put in the environment to observe it may be invasive. Will we be making a major change in the environment by observing it? And the second question is, are there any questions of privacy that may come up from observing the environment with such a fine scale in the future? And to be quite frank, I haven't thought about the second question. In the first question, I think you can look at it this way. Yes, there will be some changes in the environment because we're observing it. A simple example will be literally the hundreds of spacecraft that have now reached the end of their useful life that are still orbiting around the Earth. They are still there. But there's plenty of space for other spacecraft to go. But they're there, and they're making a small impact on the environment, and people now begin to worry a little bit now about damage from fractured and fragmented spacecraft, space debris. So there is a definite impact. Some of our probes, once they've at the bottom of the ocean, once they've reached the end of their life, they may still remain there. So yes, there will be some impact. I think you have to balance that off with what you hope is the positive impact that will come from much more comprehensive understanding. On the privacy issue, this is a very interesting issue that I don't think anybody has explored, because I think until last year nobody thought that the Earth observing system would have hundreds of millions of users and uses. And I think we have to look forward to the time when that might occur, and I think at that point it will only occur if we've thought through the privacy issues. The third issue is, how will this affect world politics? I don't know how it will affect it in general. It's hard to predict, except that when you have a common basis of information and a common basis of understanding of a problem, it tends over the long term to produce a more common viewpoint. And so I'm hoping that we will actually be able to knit together a greater degree of international understanding of these issues based on common perceptions of what the problem is. You can see it already in many cases, at least in the scientific community. You notice that there are about 8 or 9 big scientific powers, and the other 47 of them are little countries. But those people all, in those small countries, all have environments. They all care about the world that they live in. They all have scientists, and they all are going to participate in the deployment of instrumentation, and they will all ultimately receive the benefits of the collective information. And so such a concept of global Earth observing is one that will knit together the world scientific community, and it will bring into it, in a much more active role than in the past, scientists from the developing countries. So at least in that way, if you believe that science in some ways leads international developments of this kind, then I could have hope that perhaps there would be broader political agreement forged years later from the common understanding generated by such a system. This is the question is that why are we adding to the list new problems with this new capability when we've got serious problems that we know about: war, hunger, poverty, AIDS? And I think my answer is that if you look at what it will take for our civilization to get through the next century or two in advanced form, then we will have to attack world hunger, poverty, AIDS, war, terrorism, and the global environment simultaneously. And that one of the requirements for getting through this century as an advanced technological civilization will be to manage our environment at the global level. So we cannot avoid this obligation, just as we cannot avoid the others. Let's talk about Governor Schwarzenegger's response. The National Ocean Commission and the Pew Oceans Commission were both in general agreement that the marine ecosystems around the world and around the coast of the United States were in serious decline. That there were a variety of reasons why this decline occurred, but the primary reason had to do with our method of governance, that we had the largest ocean territory in the world. When President Reagan signed an executive order adhering us to the 200-mile limit, he doubled the size of the United States, and half of it's underwater. We didn't have the slightest conception how to govern this vast new territory. We didn't know who lived there, namely the fish. There weren't any voters. Various government agencies and interests played a role in which they interfered with one another, and there's imperfect and failing regulatory regime. They also recommended, both the Pew and the National Oceans Commission, that there be a doubling of the expenditure on ocean research, with a major fraction of that doubling going to the construction of ocean observing systems, so that when the decision makers finally get the act together, they will know what is going on. That report, the National Oceans Commission report, was then circulated to the governors of all the coastal states, and the governors were asked to respond to the national ocean recommendations. Governor Schwarzenegger's response was amongst the strongest endorsements of any of the states. And in fact, California can be justifiably proud of an advanced governmental system for governing its state waters, even though we can't be too pleased yet with the results. But we have created marine protected areas, and we've done a number of things. The governor's response, then subsequently on December 18th, a Saturday, the president responded to the National Ocean Commission's report. And while there was much said in the response, there was only one action defined, which was to create a National Oceans Council to coordinate the work of the many agencies, and not much was said about the rest of the recommendations. So it is clear now that California has a stronger interest and stronger political support for good management of the oceans, our coastal oceans, than is contained in the national response. It has often been the case in areas like air pollution that California has led the rest of the country. So the question I would put before the electorate, and with the hope that Governor Schwarzenegger would listen, is do you want to have the most advanced system for understanding and managing our waters off the coast of California of any in the United States? It is possible. It's not only Scripps, but many other institutions here in California could provide the observing basis for that advanced management system. Have any of the proponents of this large system come up with estimates of the cost? I think the most important thing to say is that the United States spends, on the average, about $2 billion a year on global Earth observing capacity, maybe 2.5, and that the rest of the world spends about the same amount. And that the first stage of the global Earth observing system will simply be to knit together those things that we are already doing or those things that the nations have on the drawing board, such as our Ocean Observing Initiative. And the real issue then is to take what we are doing at the present time and unify the information resource that we generate from it. The additional cost for doing that is not yet clear, but it is probably smaller than it is in the maintenance and deployment of the existing systems. But right now, if we were to tie together what we're doing better than we are, we'd have a much better system. So I think that you're looking at the present time in the United States at marginal cost increases that should be for information management about 30% of the total system, I would guess. But I suspect that that kind of money is not going to be appropriated soon. But there will be an effort to tie it together. So it's not as expensive as it looks. A lot of it's already being done, surprisingly. There's a large amount of infrastructure and scientific equipment and understanding that's already been generated. Will there be small business involvement? The answer is there certainly can be. And this is my hope when the system starts to develop its capacity to reach millions of users rather than thousands. Right now, there have been demonstration projects. I remember one that we did at NASA in which Robert Mondavi came to us and he asked, can we map where the phylloxera is affecting the roots of his vines? And the answer was, with the the hyperspectral sensor and thousands of wavelengths, you can tell the slight difference in soil color above the affected vines, and he could identify which of his plants are in trouble. And I think that kind of thing will, this led to ideas that are already out there. The advanced agricultural community will put and has put GPS on all its tractors and its planters. And they can use remote observations and actually mathematically, if you will, mathematical precision, both plant and then subsequently put the pesticides where they plant and not any other place. So that there's a great possibility for much more efficient deployment and use of our resources just from these kinds of information technology. Thus far, these have mostly been demonstrations. They've been sort of financed by the government as market building exercises, market identification exercises. And if I were an investor, I would be watching very carefully this Earth observing enterprise to ask at what phase is it going to take off, and the people who need the information start generating it themselves or going to experts at their local university or whatever and say, we need this, can we do this? And at a certain point, there'll be enough of it and it'll be widely enough available that people will start doing that. And then at some point, there'll be businesses that serve small businesses and make it happen.